Record. Yeah. Guys, I published our last session about basic machine learning algorithms, about linear regression on YouTube. So I will share a link after this session, and you can check our last session on YouTube. And as well, I also published our practice notebook on our GitHub repository. Let me show you. Sorry, I will close all the stuff. Yeah. As always, everything is over on our GitHub, and I'm publishing it almost immediately after the lecture. So here you can see our practice number 4 about linear regression. So please go through it and like improve your understanding of what we did previously. Also, as I told you last time, this linear regression, which we did on a real data set, which has a lot of columns, a lot of rows, was not precisely good. We actually did a little bit, not very practical approach, and we actually, how to say, we didn't do it right. Yeah, shortly speaking, we didn't do it right. We just did a toy example of data science project, and we made several critical mistakes that today I will demonstrate you how we can fix them if we are doing a real data science project. As always, let's create new project. Let's open Visual Studio Code and let's start programming. By the way, guys, as you see, every time I'm programming with you, so every time I'm making mistakes, this is really mistakes which I am doing in every day in my real work. So it's absolutely fine if you're making some mistakes, if you're doing something really slowly, it's fine. Okay, let's create a new folder. Oh, sorry. Every time I forgot how to do it. New folder, yeah. New folder, practice number 5. Oh, sorry. Practice number 5, and I will create new Jupyter notebook, practice 5.ipynb. Okay, let me close our previous exercise. So the goal of today's lecture, we will move step by step on a real project which you might be given on real work. So actually, we will take a real data set from Kaggle, and we will try to accomplish machine learning model training, machine learning model evaluation. And after that, we will just check how good actually our model is. It's the same as validation. And the data set which I actually want you to use today is this one data about prices of the house. We downloaded it during practice number 4, this data set. But if you don't know where it is located, let me show you. You should go on Kaggle. Kaggle is really good platform, so everybody should use it. We will go on Kaggle, and let me demonstrate how you can download it. Regression. Oh, house prices. Boston house prices. Which one is better? You see, there is many different data set. Pierce house prices, Boston house prices. Yeah, I think this one. This one is good for our purposes. It has 14 columns. And is this ongoing competition? No, let's choose some data set from competition, and we will participate in competition today. Yeah, this house prices. Data, and we will download, download everything. Okay, download all. Let's see. Downloads, house prices, and I will put this inside our guide tribe project. Guide tribe project, practice number 5. Let me put it here. Let's open it. By the way, I should share a link with you so you can follow along with me. This data we will use today. Oh, sorry. We have three .csv file: sample submission, test CSV, and train CSV. And we have this meta information about which data actually we stored in our dataset. We won't spend a lot of time here. It's actually doesn't matter today. Let's move directly to the coding. Since we downloaded our data, let's actually import packages as always. Import pandas as PD. Import numpy as np. Sorry. Import matplotlib.pyplot as plt, and import seaborn as SNS. Also today we will use scikit-learn, but we will import it later. Let's choose a kernel. Let's choose a kernel Python 3.11, and let's start. First of all, as always, we need to read our data, read CSV, and now we need to demonstrate a path to our data. This is a folder. How it's called? House. Oh, I should rename it. Let's rename this folder to make this name a bit shorter. House prices, and I prefer use underscore in folder's name. House prices, and here we will use train.csv. Okay, let's read our data. Let me close this menu. And as always, in every data science project, we are starting with EDA. As you remember from our previous session, EDA is exploratory data analysis. The first stage of every EDA, you just need to watch your data. Let's just check what we actually have here. We have 81 columns in our data. Oh, yeah, by the way, when we are reading a data, we can pass additional argument. This is index column. Index column, let's use ID. Yeah. You see right now ID column is the same as here. We just passed this argument. Okay, we have 80 columns. The first one is ID. And some of these columns are numerical, some of these columns are actually strings. This is objects. To work with this data, first of all, let's understand how many numerical columns we have and how many columns of type object we have in our data. For this, we have a special method. PT. pdf.datatypes. We just open this. We see data type of each object, but right now it is actually not really suitable, not really good for us. We cannot filter the objects which is numbers, which is integers, and we cannot filter objects which is actually object, which is strings. So to do so, we need to filter somehow this dataset. This is another dataset which has only 2 columns. So to do it, let me actually try this filtering mask. The types equal to int64. You see, this is a type of logical mask, and we apply this logical mask to our dataset. And right now, we were able to filter all the data frames, which is all the columns in our data frame, which has data type of integer 64. And let's actually count the number of such columns using len. We have 34 columns which has data type integer. Let's actually store them as a list. To do so, we will use method toList. toList. Let's see. It is a wrong way. We need to call index. Index. Yeah. Right now, instead of having data frame where first column is a name of a column and the second column is actually data type, we will just store a list of columns which has a particular data type int64. Let's call them int columns. Int columns. The next stage, in the same manner, we will store all the column which has data type float 64. Float 64 is just a decimal number. Decimal number like this, 65.0. Or maybe some other, no, I don't see it right now. Let's store them as float 64. And we will call this list float columns. Float columns. And the last type, we need to store object columns. Object columns. We need to search for data type equal to O. O is the alias for object. It's just a short name of object. Let's execute the cell. Let's see what do we have in each of these columns. I will just print the shape of these lists. We have 3 lists. So right now we are just understanding how many different columns of each type we have in our data. Len, I will call method len, just a length of a list. Okay, let's print them. Yeah, you see, we have 34 columns of type integer, 3 columns of type float, and 43 columns of type object, which is actually strings. As I told you previously, when we are dealing with with some machine learning models, they were not able to work with strings. If you're working with linear regression don't understand what is path. It don't understand what is reg. Linear regression understands only numbers. You should give them a numbers, 8,000, 9,000, and so on. So what do you need to do to transform your strings into numbers? For this purpose, we already will use scikit-learn. Let me call this this paragraph is transforming strings into numbers. The task right now is to do something with these 43 columns, which is actually a strings. For this purpose, from sklearn, let me do this from sklearn. From sklearn data preprocessing, from sklearn preprocessing, import, how does it call? Label encoder. Yeah, we need label encoder. And another encoder that we need is one hot encoder. Okay. First of all, let's have a look at these object columns. Let me call my data frame, and I just pass these object columns as an argument. We will see how they looks like. Yeah, each of them is a kind of a string. Right now, we need to understand how many unique values is in each of this column. So if column has many unique values, most probably we need to use label encoder. If column has not really a lot of unique values, we prefer one hot encoder for these purposes. Okay. Oh, sorry. I just opened something strange. For this purpose, we will use standard pandas method value counts. Oh, value counts. No. Unique and unique. I'm sorry. Yeah, right now we printed out the number of unique values in each column with a type of object. You see, the majority of them has a small number of unique values. If the column has not a lot of unique values inside it, it is called categorical column. What does it mean, categorical column? The good example of categorical column is gender or sex. You have women's and men's. You have females and so on. So you have, this is a kind of category. It does not have a lot of unique values inside this parameter. Another example is color. So for instance, you have a dataset about cars, and category for these cars will be red, blue, green, and so on. So this is also a category. Category is a type of a column which has not a lot of unique values, and these values cannot be sorted. What does it mean? You cannot say that green color is bigger than red color. You cannot sort them. You cannot say that black color is bigger than white color. These columns are kind of category which cannot be ordered to each other. In the same way, you see that each of this column is a kind of cannot be sorted with respect to each other. For instance, if you try to like sort this column, I don't know which one. Yeah, shape. For instance, shape. You don't know which is bigger, which is smaller. It is not sortable. And if it's not sortable, most probably this is a category. And when you are dealing with category, you need to encode it into the numbers. Let me demonstrate you how you can do it. By the way, let's check more accurately. Yeah, I would say that all these 43 columns is categorical one, because the biggest number of unique values is 25, and 25 is still a category. It's still not a lot of unique values in it. Okay, we will use label encoder. Label encoder. And to use it, as always in sklearn, we need to create instance of it. Instance of a class. Instance of a class encoder. Let's call it encoder. I just created this variable, and this variable called instance. And encoder has method which is called fit transform. Okay. First of all, I won't use all the columns. Let me demonstrate you how this method working for one column. Let me choose some column which has 4 unique values. For instance, this lot shape. Before we encode this column, df from lot shape value counts. You see, before we encode this column, you have 4 unique values, and this unique values is reg, er1, er2, er3. Actually, I don't know what does it mean. We just see that it has 4 unique values in it, and this is not a numbers. After I will apply fit transform method to this column, I will pass it right here. You see, this column already transformed into a vector. Let me call this variable transformed column. Transformed column. And if right now I will try to call method value counts, most probably it won't work. Yeah, it won't work because this is a vector. I will need to transform it into PD series. And right now it should work. Yeah, you see, before I applied a transformation, it was a strings. We have 925 values of reg, 484 of er1, and so on. After I transform this column using label encoder, instead of a string variables, I have numbers 3, 0, 1, 2. So you got the idea that we just changing a strings with a categories represented by numbers. And in the same manner, I can demonstrate you how this encoder will work with another categorical column. Let me choose column neighborhood. From our analytics, we see that neighborhood column has 25 unique values in it. Let me see how much of each category it has. I will use value counts. Yeah, you see we have many different type of neighborhoods. Old Town, Edwards. I think this is a kind of a regions in this Boston region. Okay, if right now I will apply a transformation label encoder on it, we will see that how these 25 neighborhoods transform into numbers. This is pretty straightforward. I will copy paste the name of a column. I will use encoder fit transform method. Let's see. You see, instead of a strings, we got a big kind of a big vector of numbers. Right now, let's save me into a variable transformed neighborhoods. Yeah, let's do it like this. Transform neighborhoods. Let's transform it into series, pandas series. It's just for simplicity to apply method value counts. Yeah, you see, we have exactly the same numbers of each category in it, 225. But right now, this is already a number. It's not a string. And if it is a number, we already can work with it, and we can already pass it into our machine learning model. For instance, linear regression. Okay, This how I did it using only 2 columns. But you may say that we have 43 categorical columns in our data. So yeah, it's pretty easy to do so. We will call our encoder method fit transform. And instead of passing 1 column, we will pass all of them. I stored the name of this column in this list. This list has 44 names of a column inside it. And it's not working. Why it is not working? You should be 1D array. Crazy. Let me see what is wrong here. I got some strange error, which I am not expecting to see. Yeah, actually, I should do it in a for loop. Okay. For call in object columns. I will go in a for loop through all of my columns, and I will try to transform them and store all of the result inside one dataset. Okay, object columns. I will call data frame from this column, and what else do I need? I need to use this encoder fit transform. Transformed df. Yeah, we will do like this. And right now in transform ds, we looped through each of an object column, and we, instead of the string values, got a numbers. This is a first strategy. The first strategy called label encoding. Let me write a subtitle here. This is label encoding. Okay. Oh, I got some strange. Yeah. In 10 minutes, we need to reconnect to this meeting. For some reason, we have free version of Zoom. This was label encoding. Another strategy how you can transform strings into numbers is one-hot encoding. Okay. Guys, in 10 minutes, please reconnect using the same link, and we will continue. Yeah, the same link should work. Another method is one-hot encoding. From sklearn preprocessing, import one-hot encoder. One-hot encoder work in a little bit opposite way. Let me demonstrate you. I will took which column I should took. Yeah, for instance, let's took this one. df.loadShape. df.loadShape. It has 4 different categories, and let's create an instance of one-hot encoder. I am creating instance. I will call it OHE. It's one-hot encoder, just the abbreviation. I created instance. Let's write instance. And right now, let me use this standard method, fit transform of our df load shape column. Fit transform. Something goes wrong. Expected to D array. What is going on? Crazy. Fit. Fit df. Maybe we should do like this. I should use reshape. Yeah, as I see, reshape -1.1. Will it work? Let us see. Let's put it in p.array and then use reshape. Yeah, we created a table. Let's put it here. We used fit and then used transform sparse matrix, and then result. Yeah, guys, you see, it is not working with the pandas data frame. This df.load shape if I call it like this is a pandas series. This is a pandas series. But this one hot encoding transformation, which I'm using here, it is not applicable for pandas series. It is designed for using with NumPy arrays. NumPy arrays is a little bit of low-level type of a code. So if I put this inside an array, I will transform my pandas data frame into the NumPy array. You see, right now, this is a type of an object array. You can do it in different ways. Right now, I do like this. Maybe you can do like 2 NumPy. I hope you have this. Yeah, you can do 2 NumPy, and it will affect in the same way. And then we need to reshape our vector into another form of 1 minus 1. And you see, we had a vector which was a flat, but right now we created a column. We like rotated it, transposed it. And when we transposed it, we can already pass it into our one hot encoder. You can actually check the documentation of this method. And you see that it is kind of working with only NumPy arrays. And instead of getting categories like we had here, it was categories from 1 to 24 because we have 24 unique values in a column. One hot encoder already coding it at a 0 and 1s in this way. So 0, 0, 1. What does it mean? That this column has 0 in A, 0 in B, and 1 in a column C, in a third category. So if we had 4 unique values, it will create 4 columns. 4 columns, and each of this column will have a binary value, 0 or 1. To demonstrate it, actually, I need one more argument, fit transform. Let me check how it is called. Fit params result to list. Is it working? Oh, it's not working. To NumPy array. Right now we have a sparse matrix inside it, and we actually cannot display it. PD series. I transform the data, but it is not displayable for some reason. You see, we can see a shape that this data is already 4 columns and 1,400 rows, but it is in a compressed sparse row format. Okay, let's try to do it in another way. PD get dummies from df dot load shape. Oh, yeah, you see, this is an alternative way of using one hot encoder, and it is actually more straightforward. You can try like this. I don't want to spend a lot of time here. I don't understand what's going on, but you can use PD get dummies. You see that previously we had one column which has 4 different values for each column, for each unique category. But right now, using this PD get dummies method, we created 4 columns, and in each column it is showed. Is it IR1? No, it is not. Is it IR2? No, it is not. And this is a reg. This is true. And if you will have a look at our series without transformation, let me demonstrate you. Let's use head, and also let's use head here. Yeah, you see, first value was reg, was category reg. And right now we have true value in category reg. Second value was also reg. We have true value here and false, false, false here. Third value was IR1. IR1, we have true and we have false in each other column. Fourth value was also IR1. We have true and false, false, false. Let's try to do the same way with another column, which also was a category. For instance, I don't know, yeah, let's use neighborhood. And for neighborhood, one hot encoding is actually not the best idea. Let me demonstrate why it is so. I will take this column and I will call PD get dummies method. You see, since this column initially had 25 unique values, 25 unique categories inside it, One hot encoding for this get dummies method, this is synonyms, one hot encoding, get dummies, synonyms, produced us 25 columns. And this column, like this row, has 24 values of false and only one value of true. You got the idea. Let me demonstrate you. pd.head and this neighborhood head. Yeah, first was CR. Now, second was WinKir. Yeah, and it has true value only in WinKir column, and all other columns is false. Why it is a problem? Because if you have many categories, it will create many columns in your data frame, and it will make a more complex calculation for your machine learning models. So this method, one hot encoding, is only recommended when you have a few columns, when the number of categories are lower than 2. Categories less than 2. This is just because of dimensionality. So not to increase dimensionality of your dataset, not making it too big. And let me try to use it with all the columns which has this object type. df.object columns. Let's see. Yeah, you see, I took 44 columns, which we expected to have a string type. And then I applied this one hot encoding transformation. And I end up with 251 columns using this transformation. And this is already numerical. This is true or false. Guys, we need to reconnect in 1 minute. So please reconnect using the same link. I will stop and see you in 1 minute. Okay, let's continue. So there are two strategies how you can transform categorical variables, which is strings, into numbers. Right now, we will try to combine them. And if a column has more than 10 unique values, we will use label encoder. And if a column has less than 10 unique values, we will use one hot encoding. This is true false. Let's actually try to do one more detail as int, maybe as type int. Yeah, you can also add this piece of code to transform true false, which is Boolean values. This is logical type of values into integer numbers. And this is actually how you can, instead of strings, get a numbers. Okay. So the next part is transforming our data. Let's have a look one more time on our object columns. And let's calculate number of unique values in it. And unique. Yes, as I told you, we will filter columns which has more than 10 unique values. Now let's use this mask, and we will. Yeah, and let's actually create a new data frame. Number of categories. We will take this data frame, and if number of categories is more than 10, let's see. Yeah, we have only 3 columns, which has number of categories bigger than 10. But as I told you, if we will try to use one hot encoding, we'll have 25 plus 15 plus 16, which is 56 columns, and our data frame will become really huge. So for these columns, it is better to use label encoding. Label encoding columns. And for other columns, I will create another logical mask, which will have just the sign lower, less than 10 values. It will be not label, but one hot encoding. these columns will be encoded as 0 and 1s. Okay, I created two new lists. This one of 3 values and this one for the 40 other object columns. Now let's have a look at our untransformed data frame of 80 columns, and we will take our label encoding columns and we will use method apply. And in this apply, we should use let's actually create new instances. Label encoder. Label encoder will be equal to label encoder, and one hot encoder equal to one hot encoder. We will create two new instances just to make it clear. And for columns which we trying to encode as labels, we will use this label encoder. Apply label encoder fit transform. And let me uncomment this part of the code. We will get an error. Yes, we get an error. How to avoid it? Why it is not working? Let me see. Index 25 are not in columns. Let me check. What is wrong with label encoder right now? Okay, let's try to do maybe like this. Label encoder. Apply. Yeah, we're using apply. Okay. Something is wrong. 25. I can encode using label encoder one column for no problem. But how to encode all of them? df.neighborhood. df.neighborhood. And I will use label encoder. Right now, I just cannot, for some reason, transform many columns at once. I can transform one column, but if I am adding two columns, if I am adding another column, for instance, I don't know, lot shape, it's giving me an error. If I'm using two numpy, we'll transform our data frame to numpy. Should be one day array, but got array of a shape of another shape instead. What is wrong with label encoder? Okay, let's try to Google it. I don't remember how to work with label encoder. This is a normal situation when you don't remember what is going on. It has method fit, label encoder, several columns. sklearn. Let's have a look at our apply. Fit transform, one hot encoder. Snip transform. Oh, it's kind of a big code for label encoding. It's not supposed to work. Multiple column encoding, robust scalar, one hot encoding, column transformer. Oh, this is kind of complicated. Get dummies. label encoding. This piece of code is supposed to work with multiple columns, but I already used it. We will use object columns. It's funny. Oh yeah, it's worked. Okay, good. Right now, yeah. Let me see. Yeah, actually it worked. We transformed all of our object columns using label encoder. But this is not I was expecting to do. I was expecting to transform only columns which has not a lot of categories inside it. So let me restart my working kernel, and we will run all the cells beforehand. And instead of object columns, we will use only label encoding columns. Let me do like this, label encoding columns, label encoding columns. And for our one-hot encoding columns, we will use method pd get dummies of these columns. So we applying two different strategies to transform our data. Part of the columns will be encoded with label, actually three of our columns. And another part will be transformed using one-hot encoder, 40 of them. In real practice, actually, you are free to choose which method you will use. And this two is the most standard one. And actually, I don't remember if there are any other strategies how you can transform numbers. Once again, what is going on? Label encoding columns. Oh, maybe something wrong with this label encoding columns. Yeah, actually, the error is here. Instead of using a normal list, here, I used a pandas series. You see, this is a pandas series. And when I'm trying to use this method, it is expecting to see not a kind of to list. I need not to list index. It is expecting to see a list and not a pandas series. So in this part of our code, when we creating two different set of columns, we need to add this index filter. And right now, this is already a list of columns and not a series. Okay, let's see. Yeah, finally, we were able to succeed. Let me restart one more time to make it clear. Rerun all, and we will see our transform that. Yeah. Label encoding columns. I'm using df. German, what is an error? Do you know?
No, I don't know. Teacher.
Teacher. Oh, it's transformed. Label encoding columns. Apply label fit transform. Okay, it's transformed. And this one. Yeah, it's working. In this part of the code, pd get dummies. I see. pd get dummies. Okay, I see. The error, yeah, I got what is the problem right now. We had 40 columns which we are trying to transform using one hot encoder. This is 40 columns. And after we use this transformer, we will end up with 195 different columns. So, and we here trying to assign this 195 different columns to the 40 columns. And the shape of these columns is not the same. We cannot like replace 40 columns with 195. This is not a good way to do so. So let us concat these 195 columns with our initial data frame. Our data frame right now looks like this, and we will try to pd concat df with let's call this variable one hot encoder data frame. No, data frame after OHE, after one hot encoding. Yeah, we have this piece of data frame and we will try to concatenate it with our initial data. Yeah, and x is equal 1. Yeah, you see this pd concat method, I am just took our initial data frame and merge it on the right side with our data frame, which is transformed. Let me prettify this piece of code as type int. I will transform all the variables in this data frame to integer. I will put this piece of code here. Then I will do pd concat. And right now, I also need to remove the columns which has object type from our data frame. Let me do like this, drop. And I will pass as a drop one hot encoded columns. X is equal to 1. Yeah, you see, finally, we finished with processing of our data frame. And right now it has no string type of a columns, no objects. And instead of having 80 columns, as we had initially, we have 235 columns in it. Let's call this data frame train, df.train. This type of data we will use, no, df preprocessed. We will call this data frame preprocessed. Okay, finally, we already finished with our preparation. Let's move to another part, model validation. Train test split. Train test split. Remember last time we just took a data frame and we trained a linear regression using all the numerical features. But we actually did it in a wrong way, because in real practice, you need to put some part of your data aside. You need to split your data. One part of the data will be used for machine learning training. Your model should be trained on this part of data. And another part of data you should use for model validation. Actually, this part of data, you never show this part of data to your model. Model should have no idea what is going on in this test part of your data. You need to split it. And this test part of your data will be used for model evaluation. You will evaluate how good model right now understand a real world problem. To do so, you will need to use several methods from scikit-learn. From sklearn, model selection, import, train test split. This method train test split allows us to divide our data frame into two separate parts. One part for training, another part for testing. Let's have a look at train test split method inside. You see, as an argument, this method took test size, train size, shuffle, stratification, and so on. Today, we won't speak about what is stratification, what is shuffle. We will use just these two parameters, test size or train size. Let's call this train test splits. We will use this method for df preprocess. You see, if I am doing it like this, it already creates me two data frames, this one and this one. And the second data frame has 365 rows in it. So the first one has approximately 1,100. Let's specify a number of test size. The test size will be 0.25. What does it mean? That 25% of data we'll put aside to use it for model validation. And we will call it df.train and df.test. Yeah, we will do like this. Okay, let's execute this. And then actually, let's fix random state. Fixing random state equal 1 or random state equal each other number. This is just a seed. This means that we are fixing a random state of our code. And every time we will execute it, like we execute it in a 1 week, in a 1 month or whatever, it will return the same result with respect to this random state. Okay, and also I recommend to use shuffle parameter. Shuffle parameter equal true. What does it mean? That right now it will split our data with respect to index. It will take 75% of index from the beginning and 25% index from the ending. And if we shuffle, it will be just randomly shuffled. Yeah, actually, it will be how we add some randomization into our split, which is actually good for training our model because it will see general patterns in our data. Let's execute the seed must be, yeah, I just too big number here. Okay, let's use seed equal 21. Right now, let's actually inspect shapes of our data. df.test shape. You see, we have 1095 samples in training and 365 samples in testing data. This train test split is a really good strategy, and you will see how like actually it is used in many data science projects. This is a kind of a standard approach, but not the best one for model validation. Later we will talk about a better strategy. Let's stick to this. And as I told you, these 300 rows, we will never show them to our model. Model have nothing, no information about this part of data. Okay, right now, we already did a good piece of job. We did label encoding. We splitted our data. Let's actually divide it into the predictors, into the features, and into the target variable. As I see, df.train head, our target, our main parameter which we need to predict is house price. Actually, I forgot how it's called precisely. Let's have a look. For call in df columns, print call. Let's also use method enumerate and I here and I here. I just forgot which column is a target for our task. It should be called something like house price. Sale price. Yeah, our target column called sale price. Okay, let's do like this. And the standard approach, how you can actually split your data frame into the target and the predictors, is take df.train. You will take this sale column, and you will call it this is y. This is y, like in our previous lecture, our target variable. And to use x, you need just to drop it. Drop sale price. You will drop it and you specify x is 1. So it means you are dropping column with this sale price name. This will be called y train and x train. Okay, and in exactly the same manner we will do for test. Let me do like this. I will change all this df.test. Yeah, okay. Let's actually have a look at the shapes. I will print the shapes of each created pieces of data frame. Y train dot shape, x test shape, and y test shape. Let's we don't need print. Okay. I forgot it, comma here. Yeah. You see one column is a target. So this y train 1000 target variable target values, and this is test 365 target values. Okay, we already created x train and y train, and now we need to do one more thing. Which is important when we are dealing with how to say numerical features. Let's have a look. x train from integer columns. Remember, at the very beginning of our lecture, we created two lists. One of these integer columns and another is float columns. Not an index. Yeah, I forgot. Float columns. Yeah, you see, we have some columns which need to be scaled. Scaling is an operation when you subtract mean and you divide the value of a column on a standard deviation. Why is it so important? Because when we are dealing with linear regression, it will try to pessimize. It will use less values which scale is too low. You see that these values in column load frontage. Let's actually use method describe to make it clear. Describe. Yeah, you see that mean value of this column is 70 and mean value of column garage year build is 1000. Yeah, you see. So this column will be treated in a different way by all our models. Model will use column garage year build much more than column load frontage because they have different scale. The scale of one column is small, the scale of another column is big. So in the terms of mean squared error, as I told you on a previous lecture, to optimize model with respect to this column is much preferable for the model. So also we need to use scaling. This will be another part, is scaling. How you can do scaling? Also, we will use standard methods, which we will have in sklearn. From sklearn, preprocessing, import standard scaler. Standard scaler, you remove mean and you divide by standard deviation. We will create instance of the standard scaler, and then we will use two methods of this scaler feed transform ex from how it's called float columns. Let's actually use it on one column at the first place. Let's use it on maximum area. Feed transform, x is not defined, x train, because we have x train. Expected to d array. What is wrong? Reshape. X train to numpy. Why I'm always get this error? I transform it to numpy. If I try to use it right now, it will see that it has a wrong shape. And then instead of a vector, I will use a column. Reshape. Yeah, right now it is scaled. That's pretty awkward. It's looking pretty bad. Yeah, you see, initially we had values in this column max area. We have values with average of 105. Right now we have this column, scaled column. We have this scaled column, and if I will apply PD series on it, this, I need to reshape it one more time. Reshape -1,1. No, it's not working. Scaled column. If I calculate mean. Yeah, guys, I forgot one more thing. Before we transformed and did all the labels, it is necessary to check if our data has any missing values. And that's why we have this problem with scaling. Let me add another part. Sorry for that. Remove missing values. Yeah, I should check if our data x train is na dot sum, because if you have missing values, almost none of machine learning model will work. Yeah, you see some of the column has missing values. And let's calculate how much actually in total of missing values we have in our data. Yeah, in our data, we have 267 missing values at total. So we need to do something about it. This is in X train. And let's actually inspect X test. X test. Let's print it out. Yeah, we have 267 missing values in X train and 81 missing value in X test. So we need to do something about it, because if you have missing values, nothing will work. To do so, we will use method fill-in-a, and let's use some strategy. Let's have a look. You see method fill-in-a, by default, it will fill all the missing values with 0. But also you have some other strategies, is backfill, forward fill, or none. What does it mean? Backfill, you have a column of values, and if some value is missing, you will just choose the previous one and put it here. So you replace all the missing values with the previous one. If you use forward fill, it means that if you have missing values, you will take value from here and put it here. So you replace it with a value which is forward from it. Let's try to use some, I don't know, forward fill. If it works, forward fill. Sometimes it is better to use it. Yeah, you see, we succeed. We use forward fill. And the same operation we will do for X test, because X test also has 81 missing value. And we do like this. Okay, great. We did this removing missing values. And now let's move back to the scaling. Scaling is important, as I told you, for linear models. Scaling. Once again, let's have a look at our float columns. Float columns. Should be, no, how it is called? Float columns. Yeah, it is like this. And then we create an instance of scalar. Scalar equal to standard scalar. Oh, by the way, I need to import it. From sklearn preprocessing, import standard scalar. Okay, scalar. And let's try one more time to use this scalar. Let me have a look at scalar. Scalar transform. Yeah, it is pretty straightforward. Scalar fit transform of df from x train from this column. Oh, guys, I made a big mistake here, because we need to write strategy here when we apply method fill-in-a. Right now, all the missing values is filled with this string. Instead of using forward fill strategy, it is filled with string. It is not the right way. You need to write method equal to forward fill, because first argument of this function by default is a value with which you want to fill all the missing one. And I passed as a first argument this forward fill. So this is not a best strategy. You need to use this argument forward fill. And to make it work correctly, I need to re-execute this part of my code. Let me actually bring it together and print the number of missing values. Yeah, let's see if I do everything all right. To check actually that everything is all right, we need to check if all the float columns has this type. We will check the types of our columns. Right now, after all the preparation, we expect that all of our columns has a numerical type. It should be integer, float, or whatever. Let's see. Yeah, it's okay. We did so.
Димаш, может, на русском, в принципе.
Блин, ничего себе. Слушай, у меня запись тут идет. Ладно. Окей. Ну, давай, поехали тогда дальше. Теперь мы должны как-то этот скейлер натравить на них. Как же это сделать? У тебя что-нибудь получается?
Я записываю. Я вот с той лекции, когда пытался все за тобой делать ручками, ничего не получилось. Ну, в плане того, что как бы все работало, но как бы отложить знания лучше просто записывая, а потом уже как бы знания больше приобретаются во время ДЗ. То есть я смотрю лекцию, записываю в тетрадку, типа как бы в целом осознаю общую картину, вид сверху, так сказать. Легче осознать, пока ты не делаешь это за лектором. Вот. А когда уже ты так вид сверху посмотрел, скажем так, за лектором, просто позаписывал какие-то такие основные моменты, и уже во время практики на ДЗ уже все подкладывается как надо. А если просто вот так вот, как это называется, впереди паровоза бежать, стараться обогнать лектора, все записывать, ну, я имею в виду, ты как на опыте записываешь быстро, и, допустим, студент записывает за тобой, он как бы все внимание тратит чисто на то, чтобы успеть записать, а чтобы осознать это не получается ничего. Поэтому как бы я считаю, что лучше... Вот вопрос. Transforming data. Это что?
Где? Какой метод?
Это вот, смотри, сначала strings to numbers, потом второе transforming data.
Вот это вот.
Это как бы типа после того, как... вот, кто-то подключился опять.
Transforming data.
Это вот после того, как мы преобразовали категориальные в числа, мы как бы их должны как бы присобачить к датафрейму исходному или что? В чем заключается transforming data?
Вот конкат, метод конкат.
Конкатенация.
We transformed our columns and we concatenated them to our data frame. And we dropped columns which has string type. Transforming data has two stages. First, transform strings into numbers. And second, you scale all the numerical columns. This you're using scalar on your data. So yeah, transforming data, it's like a big paragraph here. Let's have this number 2. And it has two stages that you do this subparagraph 2.1 label encoding plus one hot encoding. This is one part. And another part is, this one is also that you check for missing values. 2.2, remove missing values. And this will be 2.3 that you do scaling. After you removed all the missing values, you do scaling of all the numerical features. And right now, let's actually check how much numerical features we have. All our data frame right now is numerical, but some of these features is still categorical. So to find which features has kind of continuous type of data, we need to calculate number of unique values in each column. And unique. If column has more than, 100, like this area, it's definitely a continuous variable, and we need to scale it. This frontage, most probably, this is also a numerical data. So if column has a lot of like more than 50 unique values, it must be a continuous type of variable. Let me show you. And unique more than 50. How much columns do we have in it? Index. No, not like this. Extrain and unique. Let's do like this. Yeah, it's not a lot of column here, but you see that each of this column has many unique values. 660, 605. So these columns should be definitely scaled. This is columns to scale. Columns to scale. Let's see. Extrain from columns to scale. I should call index here. I forgot. Yeah, all of this column has different scale. One of them are big, another small, and we need to prettify them and make them actually on the same scale. So they should be all the same. So to do so, let me check how does the scalar work. Scalar fit transform. It's supposed to work like this. I just create an instance, scalar. Let's try to use another scalar, min-max scalar. I suspect that something is changed in this version of scalar fit transform of our data. Oh, yeah, it's scaled. If I'm trying to choose a scalar to standard scalar, yeah, it's also work. Okay. It's strange. Why we got an error last time? Xtrain is okay. And Xtrain through columns to scale, I will assign it to this transform columns. Okay. Here I am calling method fit transform and scale all the columns which has more than 50 unique values. This is just an heuristic that I am seeing that columns which has more than 50 values is continuous type. It's not categorical. So if it's not categorical, I will need to scale it. So here I'm creating an instance of standard scalar, and I am call method fit transform on this part of my data frame. And to assign it, let me create new variable, scaled columns, scaled values. Let's call it scaled values. And I will say that my Xtrain from transformed columns equal to scaled values. Okay, let's see. Yeah, and now in Xtrain, I transformed all the values. Let's have a look at them. Yeah, you see, it looks like this. And already these numbers is on the same scale. They are kind of around 1. Let's have a look. And for this, I will call method describe. Method describe. Yeah, you see, if I check mean value of each column after scaling, it is really small. It's it's 10 in power of minus 15. So the mean value of each and every column right now is the same. If I check standard deviation, right now standard deviation of each column is the same. You see, let me also add as type int. Yeah, you see, mean value of all columns is extremely close to 0. Previously, it was absolutely different. Also, standard deviation of every column is close to 1. Previously, every column has different standard deviation. Now it's the same. Minimum value, okay, 25 percentiles. So from the columns, which looks like this, terrible. It's they were all different. We end up with the columns with the same mean in the same standard deviation, which is pretty cool. Actually, we can do one more exercise. For instance, SNS pair plot Xtrain. Did I imported Seaborn? I forgot. Yeah, I imported Seaborn, so it should work. How many columns to scale I have? Sorry, interrupt. column to scale. I just called this method. I have too much columns, so my kernel is dead on my computer. Let me restart it. Let's restart. Let me comment this. And right now I want you to demonstrate the effect of scaling. Let's extrain from columns to scale. Let's took 5 of them, and we will call SNS pair plot here. This is a plot before scale, plt.show. And we will do the same after scaling. So here I do an operation of scaling, and we will try to do the same after scaling. Okay, restart, clear outputs, run all. Columns to scale is not defined. I deleted this piece of code. Sorry. Columns to scale is defined here. Columns to scale. Why is working so slow? Yeah, guys, you see, I plotted really a lot of pictures right now. Let's actually use 3 of them. No, 5 is too much. Let's use 3. Yeah, you see, I'm plotted distribution of 3 variables, which then we will scale. And you see, this distribution is extremely different. That this, for instance, column is from 0 to 300. This column is from 0 to 200,000. And this column is year. It's just absolutely different. And on this diagonal, you see distribution. And all this distribution is also different. So for model, for machine learning model, decision tree, linear regression, it is hard to work with columns which has a absolutely different distribution. And right now, if I will try to use this scaling, I will apply the scaling. You see that first of all, our mean is the same, our standard deviation is the same. And if I plot this pair plot one more time, you will see a different picture. Right now, the values of this column is much closer to each other. It's from -3 to 1. It's from 0 to 15, from -2 to 10. And previously, the difference between this value was absolutely huge. Right now, this difference is small. And this is an effect of standard scaling. Imagine that instead of standard scaler, we will apply another one. Let me re-execute this part to save these variables. Scaling. And instead of standard scaler, we will use min-max scaler. You can experiment with different scalars, but like with experience, you will understand which of them is better. On practice, yeah, standard scaler is top 1, and min-max scaler, you sometimes use it. Let's use this scalar. Let's have a look. Right now, you see that standard deviation is also 0. All the values is almost the same. And when we have a look at our distributions, you see right now, it's from 0 to 1. This from 0 to 1. This one from 0 to 1. So from the like values which all is extremely different, we finished with the values which all of them from 0 to 1. This is a kind of a good way to train your model. Okay, guys, right now we did several stages. This is about transforming our data. We encoded all the categorical variables. We did train test split. We removed missing values. We did scaling for all continuous variables, for all variables which is supposed to be numerical. And let's have a look at our data after all these transformations. Oh, okay. Also, I forgot one more thing. You see here, I used scalar, and I use it only on training data. But also, we need to use it for our test data. Scalar values test. Let's call it scalar value test. fit transform, and instead of xtrain, I will use xtest. And also I need to do so for xtest. Remember, we have two sets of data, training data and test data. Training data has approximately 1000 samples and testing data has approximately 400. So scaling, we need to do it for both parts of our data. I think it's kind of understandable. Okay, let's do this. We did scaling. We checked, we checked this one. We checked training data. Let's check also test data, how it's look like after scaling. You see, we have 365 samples and also mean and standard deviation equal to 0. Okay, now we did almost all that we can do in a pre-processing part, in transforming our data. Now let's move on. And the next part will be actually training different models. Training a model, finally. Training.
Can you describe to us what the main parts were in the lecture and divide them into smaller parts to understand us?
Okay, let me reiterate. Today we are speaking about pipeline of machine learning project. So project of machine learning. We have this task that using some parameters of a house, some area, I don't know, which region this house is located, which year it was built, we need to predict price. This is our goal, to build a model which can predict price based on 80 other parameters, on 79 other parameters. We need to predict price. And we started the whole pipeline to actually make our data applicable for machine learning, for model of machine learning. So to do so, first of all, we need to process our data and we need to encode our object columns. We inspected that we have some columns, 43 of them is type of object. This is strings. And also it's called categorical variables. And we applied two different strategies to encode these categorical variables. So out of 79 columns, 43 is categorical. And out of these 43 categorical, we also encode them using two different strategies. 40 columns, these columns which has a low number of unique values, 5, 2, 2, 4, we transformed them using one hot encoder, where I did it, one hot encoder. For columns which has less than 10 categories, we used one hot encoder. And for columns which has more than 10 categories, like this, neighborhood, or executor first, exterior second, exterior first, we applied label encoder. So this was a first part, how we transformed our data. We preprocessed categorical variables using two strategies. Second part, we scaled this label encoding plus one hot encoding. And next, we scaled our numerical variables which is continuous. And for this purpose, we also can apply two strategies, but we end up with min-max scaler. And to do so, we just picked up all the columns which has more than 15 unique values. We said, okay, if column has more than 15 values, most probably this column is continuous, like numerical. And we scaled them. Right now, starting with 79 columns, we end up with, let me check, xtrain. Right now we have 233 columns. So we started with 79, but after all preprocessing, after all scaling, the number of columns is increased. And still, we have our target variable. This is yTrain. We need to predict this one. So we will use these 234 columns to train our model. Our model needs to understand if you have this number of rooms, this area, this neighborhood, what will be the price of a house. Also, this stage with train test split, it can be done after we applied all the transformation. So, for instance, I can like took it. Sorry, how to do it? Yeah, I can like do like this and put it on backside after we transform our data. But I prefer to put it here. We also splitted our data on two parts. One part is 75% of data, and it will be used for training. We train our model. And next part is X test. It will be used for evaluating our model performance. That's all that we did so far. And right now, we did all the necessary preparation for training and evaluating our model. So we are starting our part number 3, I say. This is part our 3, training a model. Okay, hope it's a bit more clear right now. Let's start with our models. To train a machine learning model, you need to import it. How you can import model from sklearn. And right now, you need to choose which type of model actually you use. First of all, let's try to use linear model. Linear model. Import linear regression. Linear regression is one of the simplest but still very useful machine learning model. To use linear regression, we need to create an instance, like with scalar, like with label encoder. Linear regression instance. We create instance, and now to train a model, it is really simple. You call this instance method. Oh, I should call it LR. LR is linear regression. We call instance of this method, and we use method fit. Fit X train and Y train. You see what is happening in this row. You give a model all the parameters of the house and the prices of the same house. And you ask the model, please, can you find some patterns in our data, some dependencies from which you can actually estimate a final price of the house. It's like training a child. You showing a child some objects, and then you saying how does this object called. For instance, this is an apple, and your child should remember. And then after we do this operation of training our child, our linear model, we will give it a test. We will give it exam. And to do it exam, we use a test part of our data. Right now, we only training our machine learning model on a train part of data, on a 75% of data. Let me write it, 75% of data, because we did splitting. We split it on a train and test parts. Okay, let's fit our model. Let me execute this cell. You see, if you see this, it means model is trained. Okay, right now we trained our model. What we can do with our trained model? First of all, we can check coefficients. We can check intercept. I don't think it's really interesting for you, but this is a coefficient of linear regression. Since we have 240 rows, something like this, you have 240 coefficient. Let me check exact number. Yes, we have 234 different coefficient for linear regression. Okay, this is not interesting. Right now, we can evaluate the performance of our model. To check the performance of our model, we can use lr.score. And now already we will give a model our X test and Y test values. This is already a kind of exam for a model. We examine how good our model in predicting real world problems. Examine. Yeah, you see, this is a score of our model, and this is minus 0.61. Do you know what does it mean? Actually, I don't know, but yeah, actually I know, but we cannot interpret it in a good way. This is R2 score. This is R2 score. This is called R2 score. And if it's minus 0.61, this is a really bad model. Our model is total trash. What else we can do with trained machine learning model? We can do prediction. Predict. Let's predict. And to predict, we need to pass a parameters. How does it happen? You give a model all the parameters and ask him, can you please tell me what will be the price of this house based on these parameters? Since our model already saw a lot of pairs of prices and parameters, right now it has some understanding. So we can pass X test to our model, and we will predict Y predicted. Okay, let's see on our Y predicted how it looks like. Yeah, see, it's just a vector. It's just a vector which has, let me see, length, which has 365 estimated house of a price. We made a prediction. This is a prediction of our model. What we can do, we can actually compare prediction of our model versus real values which we have. We have Y-pred, and also we have Y-test. Y-test is a real values of house prices. And also you see it's 365. How we can compare them? For instance, we can plot SNS plt dot scatter. Plt dot scatter. We will plot Y-test with Y predicted. Y predicted plt dot show SNS set style white grid. I think let's call like this. Yeah, plt.scatter. And also let me pass one more parameter, plt.figure, fig size equal to 6 by 6. And let's increase DPI to 200. Okay, you see, this is a performance of our model. This is on, yeah, actually I need to add names of Y and X axis to make it more clear. plt.x label. X label equal to, on X axis we have real price in USD, real price. And on Y axis we have predicted price in USD. Y label. Is it okay? Yeah. You see, right now we are comparing real price with a predicted one. And you can actually see that if our real price is 4 million, yeah, is it for me? Yeah, $400,000, but our model predicted something like 350. Okay. What else we can do? We can just compare predicted values with true values by our own eyes. For this purpose, let's create PD data frame. PD data frame, and we pass a dictionary. Y real, it is Y real, and it will be equal to Y test. And this is a real prices, and we can add Y predicted equal to Y pred. Let's have a look. Pred df. I will call it predicted data frame. We can have a look how actually this values is looks one to each other. For instance, Command plus. Let's make it a little bit bigger. We have a price. We have a house with ID 881. Real price for this house was $157,000. But our model, our linear model, expect that this house has a price of $269,000. Okay, this is a kind of an error. We can add one more column, which we'll call error. Absolute error. And to calculate absolute error, we need just to subtract from Y real, Y predicted. Y predicted. Y real is not defined. Why it is so? Yeah, I need to use data frame here. We added one more column, and let's add one more column and call it percentage error. Percentage error. And to calculate percentage error, we just need to do like this, but also divide it on a real value. On a real value and multiply by 100. And to make it like looks better, let's also use np.round. np.round to just decrease number of decimal places in this arrow. Okay, let's have one more look. You see, right now we displayed real value of a house, real price of a house, predicted price of a house, how our model see. We estimated absolute error that, for instance, for this house, our error is $100,012. For this, $83,000, and so on. And then we added one more column, percentage error. That for the first house, our model missed 71% of price. For second, 40%, 29%, and so on. What else we can do? How we can analyze the result of our model? We can plot the distribution of percentage error. Let me demonstrate you. I am took percentage error results. Right now we are on a stage of let me write it model evaluation. Right now we are checking how good our model is, and we have different approaches how to do it. First one, we just visually have a look how our points lie to each other. Then we can actually do this data frame, and from this data frame we can estimate different parameters. For instance, let's plot SNS distribution of percentage error. Dist plot plt.show. You see, this is a distribution of our percentage error, and let's also add a mean value here. plt.rx vertical line equal. We will calculate mean percentage error like this. So our model on a mean error of our model is minus 45%. So almost every time the price predicted by our model is bigger than the real price. Okay, that's actually not really good model, but this is a baseline. Let's add this mean value. I will create mean error, and we will plot it here. Color equal to red. Label equal to mean model error. Okay, you see, this is a distribution of our errors. You see that in a perfect case, our error should be 0. But right now, our error distributed like this. So for some houses, we errored almost 200%. For some houses, we errored minus 50%. On average, our error is minus 47%. This is a plot of error distribution. This is also a good practice to look at it and estimate how actually distributed errors. plt.title errors distribution plot. This is errors distribution plot. Okay, what else we can do? We can actually plot a distribution of absolute errors. This is the same way. I will copy paste this piece of code, and instead of percentage error, I will use absolute error. Absolute error, and instead of mean percentage error, I need to use absolute error. Percentage absolute mean error. Let's execute this piece of code. Yeah, right now already this error is measured not in percents but in dollars. absolute error in count. Okay. So in dollars also, we every time overestimate the price of our house. Okay, this was a visual analysis of our model performance. You can plot this type of graphics. Let me decrease the DPI. You can plot this type of graphics. You can plot error distribution, and you can plot absolute error distribution. Let me add also absolute here. Absolute error distribution. What else? Also, you can use a matrix. As I told you previously, matrix is just a number which allows you to check how good one vector versus another. One vector is true values, another vector is predicted values. To use matrix, we need sklearn dot matrix, and for the problem of regression, we will import what do we need to import? R2 score, mean absolute percentage error, and mean squared error. We will use these two metrics as MSE, as MAPE, and as R2. Okay. Right now, we imported three metrics, so we can calculate three numbers and compare our true values with predicted one. It's pretty straightforward. Let's take R2 of Y test, and Y predicted. The same for MAPE, and the same for MSE. Okay, let me print out the results. For this, I will use this f-string syntaxes. Dot to f to decrease the number of decimal places in the output. Okay, you see that R2 score is pretty bad. R2 score should be close to 1 if our model is good. Let me also add R2 equal to this, MAPE equal to this, and MSE equal to this. Okay, R2 score is pretty bad. Our model is total trash. MAPE is 46%. This is a percentage. Let's do like this. Yeah, 45% of error on average. Pretty bad model. And MSE is also really huge. So right now we understand that simple linear regression, which we use like this, is not a good approach for this particular problem. What we can do here, let me also write here that this is linear regression. This is 3.1. Let's try to use another model for this particular problem. One more thing which is important. After you train your very first model, you can estimate the the importance of each parameters. Remember that inside linear regression we have our coefficients, these coefficients, and if you create a data frame pd.xtrain columns, I will demonstrate you data frame coef and another call name you see right now we printed out coefficient and the respective column of linear regression, and let me call this data frame linear regression coefs. When you are training linear regression, the bigger the coefficient with your variable, the more important it for your model. Values, sort values. by cof. By cof. By cof ascending равно false. Yeah, you see, we plotted the importance of each of our parameters. And you see, like from the linear regression, it is easy to understand which parameter is more important for your model. And some parameters has negative coefficient. So this actually less important parameters for your model. What you can do, by the way, let me add NP absolute here, because we are interested only in absolute values of these coefficients. Some of the coefficient has the value 10 in the power of minus 11, 10 in the power of minus 10. So, for instance, coefficient BMST count pour, roof, metal roll, electrical mix. This is absolutely useless columns in our data frame. Remember, we have 234 columns. And these columns has extremely small coefficient. They are just useless. We can remove them, and it will even increase the performance of our model. Let me demonstrate you how you can also plot a graphics of your coefficient importance. plt dot bar. Let's see, height. We need height. Sorry, height parameter. Cof. X, and we need x equal to linear regression name. Oh, yeah, it's too much parameters here. I need to decrease it. Linear regression and largest 10, for instance, like data frame has, sorry. Yeah, I do like this, and then I will took just 10 best values after from it. Sorry. Linear regression 10. Yeah, let's do like this. Okay. Yeah. Right now you see the importance of particular features in your model. If, for instance, we increase this number, let me see. Yeah, you see that importance of each parameter is decreasing. This one is not really, you cannot really see which coefficient it is, but you can estimate it from our data frame. So instead of using 200 features, we can remove some of them, just drop it out and use only this 20, which is the most important one. Or maybe top 50 features, just to decrease the size of our dataset. Okay, this is about linear regression. And now let's try to use another model. We will use 2 more models today, and we will estimate their performance. Another model is decision trees. Decision trees. This is another type of simple machine learning model. It is really intuitive, and it is used in many other different algorithms. To use this model, we need to import it from sklearn. From sklearn.tree import import tree decision tree regressor. Yeah, this is called decision tree regressor. To use the model, we need to create an instance, decision tree regressor. Okay, let's create an instance. Then we need to fit it, tree fit with x train, as always, y train. Then we need to make a prediction, ypred dot tree. To do so, we need to call method tree.predict, predict x test. And finally, we need to score how good is our model, tree.score. score X test and Y test. And let's use a syntaxis of F string here. F string here to F R2. Okay, you see, we trained a decision tree model. And right now, from the high level overview, our score is much bigger, 0.54. With linear regression model, where it was, we printed the score and it was negative, as I remember. Where it was, yeah, our R2 score previously was negative, really bad. Right now, it is already positive, 0.54. It is much, much better than we did before. What we can do, we can reapply all the stages which we did previously with our model. How do we do so? I just copy paste a pieces of code from here and will adapt them to our particular problem. First of all, let me create a validate decision tree. We will do a plot of y predicted tree instead of y pred. And let's see how this actually looks like. Yeah, looks a bit better than in previous case. What else we can do? We can also inspect the performance with respect to other metrics. Remember, when we worked with linear regression, we wrote this piece of code of MAPE, MSE, and R square. Let's actually do the same for decision tree. The only thing I need to change is to change this y pred on y pred 3. This is values predicted by 3. You see, right now our mean percentage error, MAPE, средняя, average error in percents is much lower than in previous case. It was 45%, now it's 22. What does it mean? Tree is working better than linear regression for this particular problem. Sometimes linear regression will work better. You just need to apply your expertise and try different methods. Okay, what else we can do about decision trees? We can plot these distributions and inspect how good is our decision tree with respect to errors. Let me copy paste these examples. What do I need to do? I just change one parameter in this function. To do so, I will, instead of y pred, I will use y pred 3. Okay, let's see if I got any errors. Okay, you see right now distribution of 3 errors looks much better, because average error right now is 22%. Our distribution of errors is much closer to 0. 0 is a perfect distribution of errors. And also absolute error is much closer to 0 compared to linear regression. So what does it mean? We tried one model, a linear regression, and we had pretty bad results. And right now we tried another model and we get much better results after all. What else we can do? Inside this decision tree model, you can work with hyperparameters. Let me check how does it look like, decision tree model. We can see different parameters inside it. Okay, sorry. How does it called? Get params. Sorry. Yeah, you see inside the tree you can play with different parameters. And right now we use it with default parameters. We just picked it up from the box and run it. Let's try to change some hyperparameters of our tree and measure its performance. Okay, let me copy paste this piece of code. And instead of just decision tree, which looks like this, I will check some parameter value. Max depth equal to 5. I will just limit it. Let's have a look. You see, I trained another tree. First of all, our tree was default parameters. Right now, it is with hyperparameter max depth equal to 5. I changed one parameter of our tree, and you see, I was able to increase the value of R2. Our model become better. What I can do, I can once again take this piece of code. Let me actually create a function. Def evaluate model, and it will take y test and y pred as a parameter. Y pred. We just use it several more times. Okay, y pred. Okay. Evaluate model. Let's call this function y test, just to not repeat myself, just to not use this code too many times. Yeah, it is working right now. And let's actually use it with our new model, ypred3. And you see right now our distribution become even better. It is much closer to 0. And let me also copy paste this piece of code. And let's see on other metrics of our model. You see right now our percentage error is 19%. It was 22% previously with previous 3. And right now it is 90%. And also we were able to increase our R2 score. So we used another model and we get a little bit better results. Imagine that I want to try another tree. I will try a tree with parameter max depth equal to 4. Okay, let's see. R2 score doesn't change. Max depth equal to 3. R2 score is a bit better. Let's see on other metrics. Let me actually put it here. Why I am not using it like this? 21%. And in the same manner, you can change some other parameter inside this. You just need to read through the documentation, and sometimes it is possible to obtain a perfect quality of your model just changing these hyperparameters. Let's try some other parameter and then move to another model. Which one should we use? I don't know. Maybe max depth mean sample split. Yeah, let's use max depth equal to 7 and mean sample split equal to 2. Okay, 0.64 and 20% of error. Let's use it like 5 and this like 6. Okay, not a better one. Let's the last try, and this equal to 4. Okay, actually this is a kind of best result we can obtain with decision trees. But let's move to another model, which sometimes is really useful when you are practicing with these kind of problems. Another type of model is gradient boosting. Random forest. This model called forest because there is a lot of trees inside it. So this was one tree, one decision tree, and random forest is just many trees. You can take 100 trees, 50 trees, and whatever. To use this random forest model, you import it, as always, from sklearn. Right now, we already need model called ensemble. Ensemble, import, random forest. And we need regressor. This is a problem of regression. We create instance of random forest regressor, and right now we are using default parameters. Okay, let me copy paste this piece of code because we will do exactly the same. And instead of tree, we will use rf. Rf the same as random forest. Let's run it. Yes, you see, actually the performance of random forest is not even better than our decision tree. Right now, inside this random forest, there is many trees working together with each other. Let's try random forest with another parameters. I just copy paste this piece of code, and the first parameter which you can play with is number of estimators. Number of estimators, n estimators is a number of trees inside this forest. Forest is a bunch of decision trees. 100 is a default. So on default, it has 100 trees. You can use 20. Let's see if I choose 20. Yeah, you see we a little bit increased our R2 score and just a little bit increased our mean percentage error. What else we can try to do? We can play with max depths. Each tree in a forest, we can fix maximum depth of this tree. Let's use max depth equal to 4. Okay, you see right now we made some progress. We played with the parameter of random forest. We used number of estimators equal to 20 and maximum depth equal to 4. And we obtain our R2 score 0.73. It is better than R2 score right here. Okay, let's try something else. What else we can play with? We can play with, I don't know. What else we can do? We can try to play with criterion. No, mean sample split. Another good parameter. It is the same as in decision trees. Mean sample split. Oh, it's make our model worse. Equal to 4, equal to 3. You see. Let's decrease maximum depth. No, it is not working. Let's use number of estimator equal to 200. Okay, actually, I think we played enough. And this is how you can play with parameters using your hands. But there is much better strategy how you can choose your parameters when you're using the model. Okay, guys, I think in 10 minutes we will finish. This is the last topic for today. You see, we tried 3 different models. I showed you how you can evaluate the performance of your model using like visual channel. You just checking the plots by your own eyes. You are checking how the errors is distributed, how close is this red line to the 0. And then you can actually use metrics, just numbers, and say, okay, 90% of error, okay, it's fine. Actually, it is a little bit like too much, but sometimes it is fine. And you can also check R square. The better R square, the closer it to 1. Okay, then we tried 3 different models: linear regression, decision tree, and random forest. And also I demonstrate you that inside random forest, you can play with some parameters like by your hands. I just choose one parameter and replace its value with something. But there is a better strategy called grid search. Grid search. Okay, let's remove grid search. This is a strategy how you can automatically choose best parameters out of all this space. You see, if I will open this random forest regressor, it has many different parameters. And I would say that nobody knows how to optimize them in a perfect way. To do so, like actually to make this process automatically without applying your own hands, you can do a for loops. You can check, is this particular combination of parameter is the best one. To do so, you need to import grid search from sklearn model selection, import grid search CV. Grid search CV. To use this grid search, you need to create an instance. Let's call it grid search CV. What does it need as an argument? It is need an estimator. It is need a grid of parameters, and it is need a scoring. Parameters grid. Remember that previously I changed the number of estimator, maximum depth, and mean sample split. Parameters grid is a dictionary where you can pass which parameters you want to optimize. Actually, I can say, please try to test a model which has 15 trees inside it, 100 trees, and 150 trees, something like this. What else? For instance, I want to optimize maximum depth. I write maximum depth equal to 3, equal to 4, and equal to 5. Please try these values. What else? Actually, let's stop here. So right now you see that my algorithm will try each combination of a parameters. It will try 50 estimators with maximum depth of 3, 4, and 5. 100 estimators with depth 3, 4, and 5. So in total, it will do 9 training of a model. And what else do we need to pass? We need to pass an instance of our model inside this grid search. Let me create an instance without hyperparameters. Also, this is called hyperparameters, parameters of a model. First of all, I give a model to here, and then I give a parameters grid. Parameters grid equal to it. Okay. Let's try to use grid search. To use grid search, you do exactly the same as you do with all other models, with linear regression, decision tree, and so on. You do method fit, and you pass x train and y train. Also, let me add parameter verbose equal to 10, and one more n drops equal to -1. This n drops mean that I will use all the resources of my processors. For instance, if I will demonstrate you htop, you see that my laptop has in total 12 cores. And right now I will use all the resources of these 12 cores. You see it right here, in order to train this model. Okay, let's see. Yeah, the process is started. And you see all my cores on this plot is right now working. They are working together. They were 100% of capacity of them used. And right now model is trained and the capacity is finished. You see here is some information that we fitted our model. We tried this combination, and this combination, and we finished training of our model and choosing the best combination of parameter. To find the best model, we just use best estimator. You see, our best combination of parameter is depth equal to 5 and number of estimator equal to 150. 5 and 150. Okay, and right now we can use this instance of grid search best estimator as just as an instance of other machine learning model. Best estimator equal to this. And we can do all the stuff about model evaluation as we did previously. We just copy paste this piece of code. I will put it here, and instead of RF here, I will use best estimator. Okay, let's call it. You see, this is a result of our best estimator. Actually, not impressive at all. We were not able even to beat the performance of our random forest without grid search. But this is a good way to automatically search for best parameters of your model. Let's actually try one more time. Let's increase number of parameters in our model. Let's add 2, 3, like 6. Oh, sorry. 2, 3, 6. 6. Let's add here 200. And let's also try to optimize something else. To check which parameter you want to optimize, you can do like this. Let's optimize. What do we need? Random state. Yeah, let's use this parameter of mean sample split. Let's also optimize it. We will pass some 2, 3, 4, 5, 6. Okay, we increased the parameter space. We will call this grid search one more time. You see that, okay, it's not working. Yeah, I got some error. Invalid parameters must be, oh, yeah, I made a mistake. This should be a float number, 0.2, 0.3, and 0.4, 0.5. Like, let's do like this. Okay, let's try. Okay, now I'm training. You see 100% of my processors is working. They are trying to train this model. You see here is some like text, output text about how many models we trained. And in total, we should train 400 models right here. You see, here is 4 multiplied by 5 multiplied by 5. So this is 80. And also we have some cross-validation parameter equal to 5. So it is 80 multiplied by 5. It is 400. Now we finished. Let's check our best estimator. Okay, it's actually even worse. So all our training end up with estimator which is even worse than the previous one. You see, and this is quite a typical situation. When you train in a model, you spend a lot of resources on its training, but after all, you are not able to beat even a simple one like this one. Okay, let me re-execute this piece of code. Yeah, it's 20% of error and high R squared, and here it's 0.5. Okay, that's all, guys. Today we moved through the essential stages of our machine learning training process. We demonstrated you how you can prepare your data, how you can encode categorical features into numbers using two strategies, label encoding and one-hot encoding. It was here, one-hot encoding. Then we did train test split. I demonstrated you that this is a good strategy for validation of your model. Then we did scaling. Scaling is important for some continuous variables. And after we prepare our data, we demonstrated you how you can train different models, linear regression, decision tree, random forest, how you can evaluate the performance of your model using visual representation, distributions, and using these metrics, different metrics. And after all, we tested 3 different models. I demonstrated you how you can automatically, using grid search, choose different parameters. You just need to choose wisely. You just need to understand what does this parameter is doing. First of all, an estimator is just a number of trees in your ensemble, in your forest. Maximum depth is the depth of each tree. Each tree has its depth, and we are trying to play with this parameter. And mean weight fraction of leaves is a proportion of how many samples will go to each node of our tree. We try to play with grid search. We fitted 400 different models at the same time, and we measured its performance. Actually, that's all, guys. That's all for today. Thank you for your attention. And on the next lecture, I think we will try one more project in machine learning, and we will try to do the same stuff one more time, step by step. So just to fix it in our heads. I will stop sharing, stop recording. Any questions?